So let's talk about the properties of light and how it affects the energy of light. One of the questions you'll have to be able to answer is being able to calculate the energy of different photons of light of different wavelengths and different frequencies. So let's start off reminding yourselves about what the properties of light are, light waves that we have to worry about. We have two significant properties we're concerned with. One is the wavelength, which is the distance between two wave crests, which is the same as the distance between two troughs measured in meters. And then we also have the frequency, and the frequency refers to the number of wave crests that pass through a given point in 1 second. We measure it in how many crests per second or cycles per second. So it has units of seconds to the -1. We also call that unit a hertz. So a hertz is a inverse second. So our important light equations that we need, there are two that are relevant. One is what relates the wavelength and the frequency. The wavelength and the frequency are related by the speed of light. The wavelength times the frequency equals the speed of light. And so we see that 3 times 10 to the 8th meters per second, which is the value of the speed of light, equals the wavelength in meters times the frequency in inverse seconds. The upside down y is referred to as a lambda. That is the symbol that we use for wavelength. And the thing that looks like a cursive V is the Greek letter nu, and that stands for frequency. But you can use the words wavelength and frequency if you get confused with the variables, the Greek letter variables that we used for those. The other relevant important information is that the energy of light is Planck's constant times the frequency. So the energy of light is related to the frequency. It is indirectly related to the wavelength because the wavelength is related to the frequency, but the energy of light equation refers to the frequency of light. And the value of Planck's constant is 6.626 times 10 to the -34 joule seconds. So with those two equations in mind, let's try a problem. What is the energy of a photon of 365 nanometer light? So note that 365 nanometers, that's wavelength. It's giving me meters. I know meters are a unit of length, so this is a wavelength. I have to be careful because my equations are going to need it in meters. So let's just go ahead and convert that. 365 nanometers times, I need nanometers on the bottom and meters on the top, and it's 1 times 10 to the -9 meters per nanometer. So that's 3.65 e to the -7 meters. Most of our visible wavelengths, which tends to be the problems that you're going to see, are going to be all in hundreds of nanometers, and they should have exponents of 10 to the -7 meters when we convert them. Okay, so we know that the energy of light is Planck's constant times the frequency. Remember that Greek letter nu refers to frequency. And when we have frequency, we weren't given frequency, so our first step is going to be to convert wavelength to frequency. So I know that 3 times 10 to the 8th is the value of the speed of light. I know that the frequency is 3.65 times 10 to the -7 meters. So if I divide both sides by 3.65 times 10 to the -7, and that value is going to be equal to 8.219 times 10 to the 14th inverse seconds. Now I should be checking my units. This frequency should be units of inverse seconds or hertz, and it is, so that's good. Another thing I should be checking is that for visible light frequencies, those frequencies between about 400 nanometers and 700 nanometers, this isn't quite in that range, but it's still in hundreds of nanometers. I expect that the exponent for the frequency should be 10 to the 14. So this is an exponent of 14. That seems reasonable, so I think that I probably did my calculation right. This is particularly helpful because if you are not using the scientific notation on your calculator, if you're trying to enter it in directly, it's very easy to accidentally multiply by the exponent rather than divide by the exponent, and you're going to get crazy calculations. It's important when you're using your calculator that you should be using the exponential function designed for writing numbers, entering numbers in scientific notation. All right, so now I'm ready to calculate the energy. Energy is equal to the Planck's constant times the frequency. So 6.626 times 10 to the negative 34 joule seconds times 8.219 times 10 to the 14 joule seconds. So we had the value of the frequency as 8.219 times 10 to the e to the 14 inverse seconds for our frequency. Now let's calculate the energy of light. So we know that the energy is equal to Planck's constant times the frequency. Planck's constant is 6.626 times 10 to the negative 34 joule seconds times 8.219 times 10 to the 14 inverse seconds. And that number calculates out to be 5.45 times 10 to the negative 19 joules. Note that my seconds units cancels. So I end up with a unit of joules. That's good. Energy should be measured in joules or calories, and so this is a consistent unit, so my units check out. Also, for visible light, most of the visible light should be in the e to the negative 19th joule range, so the exponent looks good for energy of light. I have two checks. Things are consistent, and this is how we're going to go about calculating energy of light.